The Chandrasekhar limit represents one of the most profound discoveries in astrophysics, establishing a clear boundary between different stellar fates. Named after the brilliant Indian-born astrophysicist Subrahmanyan Chandrasekhar, who developed it in 1930, this limit defines the maximum mass that a white dwarf star can possess while remaining stable. Approximately equal to 1.44 times the mass of our Sun, this critical threshold determines whether a dying star will peacefully fade away as a white dwarf or undergo catastrophic collapse, potentially triggering a supernova explosion. The profound implications of this limit extend beyond individual stellar evolution to influence our understanding of galactic chemistry, cosmic distance measurements, and even the fundamental interplay between quantum mechanics and relativity in astronomical contexts. The journey toward understanding the Chandrasekhar limit began in the early 20th century, amid revolutionary developments in physics. By 1920, astronomers had already observed that Sirius B, a white dwarf companion to the bright star Sirius, possessed a density approximately 1 million times greater than our Sun. This extraordinary compression could only be explained if the atoms forming the star were so firmly compressed that they no longer existed as separate entities, with gravitational pressures forcing positively charged ions to be surrounded by a sea of electrons. Before the advent of quantum mechanics, physics lacked explanations for forces capable of supporting stars against such immense gravitational pressures. The formal mathematical foundation for what would become known as the Chandrasekhar limit began to take shape with calculations by Wilhelm Anderson in 1929 and Edmund C. Stoner in 1930, who worked on idealized constant density star models. However, it was Subrahmanyan Chandrasekhar who, in 1931, published The Maximum Mass of Ideal White Dwarfs, incorporating hydrostatic equilibrium for the density profile and establishing the now accepted value of the limit. This groundbreaking work combined Einstein's special theory of relativity with quantum physics principles to demonstrate that a white dwarf supported solely by electron degeneracy pressure would become unstable beyond a specific mass threshold. The significance of this discovery was eventually recognized when Chandrasekhar, along with William Alfred Fowler, received the Nobel Prize in 1983 for this and other contributions to astrophysics, more than 5 decades after the initial publication of his findings. To understand the Chandrasekhar limit fully, one must first grasp the unique nature of white dwarf stars and the quantum mechanical phenomenon that supports them. White dwarfs represent the final evolutionary stage for the majority of stars in our universe, including our Sun. These stellar remnants form when stars exhaust their nuclear fuel, shed their outer layers, and leave behind a hot, dense core. Unlike active stars, white dwarfs no longer undergo fusion reactions, meaning they lack an internal heat source to counteract gravitational collapse. This absence of active fusion raises a fundamental question. What prevents these stars from collapsing entirely under their own gravitational weight? The answer lies in electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which states that no 2 electrons can occupy the same quantum state simultaneously. In the extremely dense environment of a white dwarf, where electrons are effectively compressed into the smallest possible volume, this principle forces electrons to occupy progressively higher energy states. This creates an outward pressure that balances against gravitational collapse. But importantly, this pressure is fundamentally different from the thermal pressure that supports active stars. In a normal star, adding heat causes expansion and cooling as thermal pressure increases. However, in a degenerate system like a white dwarf, adding heat increases temperature without causing expansion because the pressure is independent of temperature and depends only on density. This peculiar property becomes critically important when considering stability limits and has profound consequences for stellar evolution. The Chandrasekhar limit serves as a cosmic boundary that determines the ultimate fate of stars. For white dwarfs with masses below this critical threshold of approximately 1.44 solar masses, electron degeneracy pressure successfully balances gravitational forces, allowing these stellar remnants to remain stable indefinitely as they gradually cool over trillions of years. Importantly, all white dwarfs directly observed in our universe have masses below this limit, confirming the theoretical predictions established by Chandrasekhar nearly a century ago. When the limit is approached or exceeded, however, dramatically different outcomes emerge. A white dwarf nearing the Chandrasekhar limit may trigger catastrophic thermonuclear reactions. This typically occurs in binary star systems through one of two mechanisms. The single degenerate model, where a white dwarf accretes material from a companion star until reaching the critical mass threshold, or the double degenerate model, where two white dwarfs merge to create an object exceeding the limit. In either scenario, as the mass approaches 1.44 solar masses, compressional heating of the core leads to carbon fusion ignition. Since the white dwarf structure prevents expansion in response to this heating, a runaway thermonuclear process ensues, consuming much of the star in seconds and producing a type Ia supernova explosion that completely obliterates the original white dwarf. These standardized explosions serve as standard candles for cosmic distance measurements, playing a crucial role in modern cosmology and the discovery of the universe's accelerating expansion. The Chandrasekhar limit extends far beyond merely explaining white dwarf stability, influencing our understanding of elemental creation and cosmic evolution. Through thermonuclear fusion, stars typically create elements up to iron on the periodic table. However, heavier elements, from copper and silver to gold and beyond, require the extreme conditions found only in supernova explosions triggered when stars exceed their stability limits. These cataclysmic events seed the interstellar medium with heavy elements essential for planetary formation and ultimately life itself. The Chandrasekhar limit thus helps explain not only stellar fates, but also the chemical evolution of galaxies and the very composition of our planet and bodies. Furthermore, understanding this fundamental limit provides crucial insights into the formation of more exotic stellar remnants like neutron stars and black holes. Stars with initial masses exceeding about 8 solar masses evolve differently from their lower mass counterparts, while stars below this threshold shed sufficient mass during their red giant and asymptotic giant branch phases to leave behind stable white dwarfs well below the Chandrasekhar limit. More massive stars develop cores that inevitably exceed this boundary. When electron degeneracy pressure proves insufficient against gravity, electrons are forced to combine with protons, forming neutrons and creating the even more exotic neutron stars supported by neutron degeneracy pressure, or in cases of even greater mass, collapsing completely into black holes. The Chandrasekhar limit represents a fundamental threshold in astrophysics, where quantum mechanics and relativity converge to determine cosmic destinies. From defining the stability boundary of white dwarfs to explaining the mechanism behind type Ia supernovae, this mathematical limit established by Subrahmanyan Chandrasekhar has profound implications across multiple domains of astronomy and physics. The seemingly abstract calculation of 1.44 solar masses serves as a cosmic dividing line between stars that fade gradually into obscurity and those that end their lives in spectacular explosions that enrich the universe with heavy elements necessary for complex chemistry and life. As our observational capabilities and theoretical understanding continue to advance, the Chandrasekhar limit remains a cornerstone concept in stellar evolution models. Its discovery serves as a testament to the power of theoretical physics to predict natural phenomena decades before observational confirmation became possible. From explaining the nature of white dwarfs to providing insights into the creation of elements and the measurement of cosmic distances, this singular mathematical boundary continues to illuminate our understanding of the universe's past, present, and future evolution.